Hello everyone, my name is Chiyuan. Today I'm going to talk about our work on analyzing memorization influence in deep learning. So memorization is a ubiquitous problem in deep learning because of those larger and larger models that are being used in real-world tasks. And we know that those models can fit the entire training set even when random labels assigned for those instances. And those kind of memorization is generally uh, a concern in deep learning because it's not only related to overfitting, but it also have privacy or security concerns. However, it is kind of counterintuitive because the state-of-the-art models are kind of always larger than the previous models. So could memorization have some positive influence on the generalization performance of your model at all? The short answer is yes, which is what we study in this paper. So the main intuition is that the data in real world are naturally follow this kind of long tail distribution, which has many instances that are uh, relatively low frequent in the data. Because of low frequency, there's no pattern or structure that are shared across many examples for those instances. So the model can only memorize each of those individual examples. However, when this example shows up in the test set, because like if you memorize the corresponding training example, also infrequent training example in a training set, you are now able to actually correctly classify this infrequent test example, and this gives you benefit in terms of generalization performance. So in order to verify our hypothesis, we use the following quantity of influence defined on an algorithm A and the dataset S. The influence of example I on example J is basically defined as the probability of a model correctly classifying example J when example I is included in the training set minus the probability when example I is excluded from the training set. So this quantity is large if and only if example J can be correctly classified with high probability only when I is included in a training set. In other words, example I basically decide whether or not example J can be correctly classified. So this is strong influence. And with if we plug in J as I, we can have a notion of memorization, which is basically self-inference. Memorization, high memorization of example I basically means the knowledge from the rest of the training set cannot really help to decide the label on example I. So you have to include I in the training set in order to correctly classify the label. So with those notions, we can derive some algorithms and estimators to compute them and evaluate, rank the example according to their memorization and influence score in the data set. What we test here is whether or not those memorized examples are helpful at all in terms of generalization. So what we did is we ranked the example according to the memorization estimate, and then we remove a certain subset of examples that are mostly memorized. As a baseline, we just remove a random subset of equal size from the training set, and then we evaluate a model trained on such kind of training set. What we see here is that removing the most memorized example actually have a much larger drop of performance than removing a random subset of equal size. Uh, Moreover, we can use the influence estimate to identify which particular test example is highly influenced by those training examples that are memorized. What we found here is again, consistent with our intuition. For those highly memorized examples, most of them actually have a particular corresponding test example that is highly influenced by this training example, and the job in terms of test performance on those subset of highly influenced test example actually can explain the majority of the job in terms of performance when we do this subset training. Um, Here, I'm just showing some visualizations. The left column shows training examples, and the right columns show the test examples that are ranked by the influence of this particular training example on each of the test example. What we see here is that the most influenced example, which is the second column, are basically very similar to this training example. We can look at the top ranked, like the highest influence example pairs here. They're basically kind of multiple shot of the same scene or object. When we move lower down to the spectrum of relatively low influence, we still see the same pattern here, but now they're sometimes not exactly the same object or scene, but they're sharing some very similar visual themes here. So to conclude, we study memorization and influence in deep learning by proposing a memorization and inference estimate and compute it on real-world data. And with those mechanisms, we are able to verify our hypothesis or our intuition that memorization can actually have positive influence in terms of generalization performance on real-world data because of this effect of long-tail data distribution. So for more details, we refer to our papers, and we have pre-computed scores and code and checkpoint for download at URL on the bottom right. Thanks.